So, good evening, everybody, and thank you for the invitation to return once more to talk to Southport U3A Astro Group. So yes, this is the end of everything, and we're going to look at the near future and the far future for the fate of the Earth, the fate of the Sun, the fate of the solar system, the galaxy, and ultimately the fate of the universe. So this is going to be quite a long journey, so one way of thinking of it is to think of good old Buzz. To eternity and beyond, that's what we're going to be doing. So I'll start with a little bit of a prologue and then think about the future of the Earth and the Sun and the solar system, and then look a little further into the future about the future of stars in our galaxy and ultimately all galaxies. And then we're going to really go into the distance and look at the far, 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 far future and look at the ultimate fate of the universe. And in order not to leave you too depressed, I'll then have a little epilogue and try and leave you with something a little bit brighter to think about. So, just to recap, we are 13.8 billion years into the story, in the sense that the story started with the birth of the universe, the beginning of everything. We can think of the observable universe as being a sphere. When we look out, we can see a lot in the observable universe. At the moment, our observable universe, all of the galaxies, all the stars, sit inside a sphere which is about 100 billion light years across. But we know the universe is expanding, so all of that stuff used to be a lot closer together. If we go back far enough, everything that we currently see in the entire observable universe, all 100 billion light years of it, all of that used to be in a sphere a few centimeters across. In other words, I tend to think of this as the cosmic golf ball. It's difficult to perceive just how dense that must have been if you take the entire observable universe and crush it down to this volume, but this is how the universe started. In the very early universe, we started with everything packed into a small space. I must remember that lasers don't work on TV screens. And in the early universe, in the first 3 minutes of the universe, the protons and neutrons that make up matter were made, and so we ended up with a universe full of hydrogen, which is effectively just the particle protons in the nucleus, and some protons and neutrons got together and formed what we now call helium. So it took 3 minutes to make all of the hydrogen and all of the helium in the universe, and that has been rearranging itself for the last 13.8 billion years, and some of that rearrangement, of course, is us and the Earth and the Sun, etc. So, in order to try and make sense of what I'm going to be talking about, I use this timeline along the top. We can't sensibly talk about years or even thousands of years. We're going to be using powers of 10 in order to look further and further into the future. So each small box here at the top represents 10 times further into the future. So in other words, 10 to the power 0, that's effectively where we are now. 10 to the 10 years into the future, 100 years into the future, 1,000 years into the future, and similarly as we go on, 10 to the 4, 5, 10 to the 6, 1 million years into the future, 7, 8, 9, 1 billion years into the future. And at the end of this particular timeline, 10 to the 12, 1 trillion years into the future, using the standard trillion rather than the old-fashioned billion. So keep an eye on those boxes, because otherwise it's easy to lose track of where we are. Now, I must credit the fact that Adams and Laughlin wrote a paper in which they talked about when various astrophysical phenomena are going to occur, or likely to occur in the future. And I've used their paper to try and get my slides in the right order. So regardless of what I'm actually talking about, I am trying to present all of the slides in strict time order, regardless of whether they're talking about the Earth or talking about the Sun or talking about galaxies. So this, if you like, is a journey through time. So we're not going to start this year or next year or 10 years or 100 years. Let's assume we get global warming under control. Let's assume we don't have a nuclear war that completely wipes us out. The first point I want to make is that according to a different talk I give about the nature of what we mean by a second, the Earth is slowing down, and at the moment we are adding leap seconds to our clocks to try and keep our clocks in sync with the rotation of the Earth. If we go 1,000 years into the future, the Earth will probably have continued to slow down, and we will need to add leap seconds, not every few years, but probably every few weeks. In other words, the length of the day will be 24 hours and a bit, and we will add leap seconds every few weeks to try and keep the rotation of the Earth in sync with our clocks. Now, when it comes to looking at the future, it's often said that, well, sooner or later there's a supernova going to go off in our galaxy, and that's going to be wonderful and spectacular. But of course, we can't actually predict when supernovae are going to actually go off. But there are various things that we can absolutely predict in terms of changes that are coming our way. And one of them is the fact that we know how the Earth moves, how the Earth spins and how the Earth goes around the sun. And this particular wobble of the Earth's axis, the fact that the Earth's axis points to different parts of the sky, called precession, we know exactly what that cycle is from looking at historical records. And we know that the Earth's axis is going to point to different parts of the sky over a 26,000-year cycle. So in other words, if we look at the patch of sky that's mapped out by this circle at the top here, then we find that at the moment, on the right-hand side, that yellow dot is where the Earth's axis is pointing at the moment. The north celestial pole is right next door to the star Polaris. But that won't be the pole star for that long, in the sense that in half of 26,000 years, the Earth's axis will be pointing on the other side of that circle. And in fact, at around 14,000 AD, in about 12,000 years, the pole star will actually be Vega. That will be the closest bright star to the pole. So it'll be even easier to find north, because a nice bright star like Vega will be next to the north celestial pole. So apart from the fact that makes life easier for Boy Scouts, what does that mean if the Earth's axis now points in a different direction? Well, at the moment, the Earth is closest to the sun in northern winter. In other words, the Earth's axis is pointing away from the sun as far as the northerners are concerned, when the Earth is at its closest point to the sun because of its elliptical orbit around the sun. But when the Earth's axis is pointing at Vega, that means that we will be closest to the sun when we have a northern summer. In other words, we are tilted towards the sun, and we will be closer to the sun in whatever it is, 10,000 or so years' time. So that means our climate is going to change, because instead, at the moment, of being closest to the sun in winter, we are going to be closest to the sun in summer. So the seasons are going to be essentially the same, but a little more extreme because of these two effects coming together. And collectively, variations in the Earth's climate as a result of changes to the Earth's spin or changes to the Earth's orbit around the sun are collectively known as Milankovitch cycles. I'm not going to say an awful lot about them, but if you're interested in these things, you can just Google Milankovitch cycles and find out more. So we're now moving, again, another factor of 10 to the 5 into the future. We've gone from 1,000 to 10,000. We're now thinking about 100,000 years into the future. The Voyager space probes launched in the 1970s are going to be passing by some neighboring stars on this sort of timescale. If you remember, in the late 70s, Voyager 1, Voyager 2 were launched in order to go past Jupiter, Saturn, and in the case of Voyager 2, Jupiter, Saturn, and Uranus and Neptune. And then both are now leaving the solar system. Voyager 1 at the top there, Voyager 2 at the bottom. According to the direction in which they're heading, Voyager 1 is going to pass by a star with the wonderful name of Gliese 445, and Voyager 2 is heading out in a different direction and is going to pass the star Ross 248 on timescales of order tens to 100,000 years or so. Pioneer 10 and 11 are also on this particular graphic. They were launched earlier, but they're going slower, so they're going to take a little longer to reach any other stars. Pioneer 10 is actually heading off in the direction of Aldebaran, and Pioneer 11 is actually heading off in the direction of the center of the galaxy. And we know that there will be repeating cycles of glaciation. Again, how do we know? From looking at historical records. There have been ice ages fairly regularly on the Earth, and they tend to occur on timescales of order 100,000 years. Now, we have recently entered a warm phase, a so-called interglacial phase, and if we know that ice ages come every 100,000 years or so, and we've just entered a warm phase, then we can predict the next ice age will be on its way on this sort of timescale, 100,000 years or so. This is another manifestation of changes to the Earth's orbit around the Sun, giving rise to climatic changes. Another manifestation of Milankovitch cycles. So you have to admit that even if man-made global warming and climate change becomes something that we can control, ultimately there are factors beyond our control that will change the Earth's climate. It's thought that in the past that the Earth actually went through a snowball Earth phase where the entire planet, not just a major part of the planet, but perhaps the entire planet was icebound. But the 100,000 year cycles are normal ice ages where the ice simply comes further south than it normally does into Europe, for instance. On this sort of time scale, 100,000 years or so into the future, the Earth will continue to slow down because of the tidal effects of the Moon. And by 100,000 years into the future, leap seconds will not be added every few years or every few weeks. Because the Earth will have slowed down substantially by this point, we'll need to add seconds to our day every day. In other words, the Earth's rotation period will no longer be 24 hours. At this point in time, it'll be about 24 hours and a second. So we will need to add a second essentially every day. Every midnight, we would have to add a second to keep the clocks synchronized with the rotation of the Earth slowing due to tidal effects of the Moon. On a timescale of 100,000 years, we can't be sure, but we think it is likely that some stars in our neighborhood may go supernova. For instance, Eta Carina, not unfortunately visible from Southport, but in the southern celestial hemisphere, Eta Carina is a very massive star which recently has been apparently blowing off a huge amount of matter, generating this nebula. It looks a bit like a planetary nebula, but it hasn't come to the end of its life yet, but it seems to be shedding its outer atmosphere as if it's looking very unstable. And so it is thought that this is getting to the point where it's not too long before it'll go supernova. So it's thought that perhaps in the next tens or 100,000 years, Eta Carina could end up going supernova. Unfortunately, it would not be visible from the UK. But another star that might be in the same category is Betelgeuse. And although this is rather fanciful, this is a genuine picture of the night sky with an observatory in the foreground, but the photographer has taken the liberty of adding an extra star where Betelgeuse is to say if Betelgeuse were to go supernova, then it could be substantially brighter even than this particular graphic would indicate. Perhaps you can just about see the rest of Orion there, just to the bottom right of the supernova. But of course, if Betelgeuse happens to explode, then it's going to completely ruin the constellation of Orion. So, you know, swings and roundabouts. It'd be nice to see a supernova, but unfortunately, Orion will never be the same. And it's thought that Betelgeuse, again, appears to be unstable and might be supernova candidate before too long. But as well as supernova, we have to worry about other stars coming to the end of their lives. You think of Betelgeuse being 600 light years away, so that can't possibly be a problem for us because it's 600 light years away. But there are some stars that are thousands of light years away. For instance, Wolf-Rayet 104 is 7,000 light years away, but potentially could still be a problem for us. On the same timescale of order 100,000 years, it might be that this star comes to the end of its life. And this is a potential danger for us because when it does die, it might actually produce more radiation than simply a supernova. Because stars like this tend to have these jets, these rapid rotation of the star and the stellar system that it's in can produce jets of material coming off in opposite directions. And if one of those jets happens to point at the Earth, then we get a big dose of radiation. Even though it's 7,000 light years away, if the jet happens to point in our direction, it could be a problem. It's been calculated that it could, in principle, sterilize the Earth if it were to be lined up perfectly. At the moment, we're not sure because it's very difficult to tell for a rotating system exactly what its axis of rotation is. So we're hoping that this particular beastie is not lined up with the Earth so that when it does die, it might produce jets of radiation, but they will not necessarily be coming in our direction. Fingers crossed. On a scale now, we've gone one notch further up. We're now at 10 to the 6, about halfway through our scale. Not halfway through the talk, but halfway through this particular scale of 10 to the 6 years. So we're talking about 1,000,000 years into the future. The sun is going around the Milky Way, as are all the stars in the Milky Way, rotating around the center. But all stars are in effectively independent orbits. So every once in a while, the sun is going to come by happen chance close to another star. So it has been calculated that when we look at the other stars in our neighborhood and try and work out which way they're traveling, which way they're moving, it looks like in 1,000,000 years' time, we are going to happen to come very close to one of our neighboring stars. Called Gliese 710, it's going to apparently come towards us and then go away. That's not its actual motion, it's just the relative motion as our sun and that star go round the center of the Milky Way. So Gliese 710 is going to get close enough such that it actually enters the Oort cloud, containing trillions of icy bodies. And as it does so, it's almost certainly going to perturb quite a few of them and send a whole load of these icy bodies hurtling into the inner solar system. So it's probably going to result in comets, bright comets, naked eye comets, perhaps one every month for 1,000,000 years, as this star comes close and starts perturbing what's going on in our solar system. So our solar system will not be dominated by one star, we're going to have a second star in the solar system. So for a while, two suns. Now, okay, not quite the same as that particular system with two suns from Star Wars, but there will be two suns in our solar system for a while as Gliese 710 passes by. This you may recognize as Meteor Crater Arizona. We're still on 1,000,000 years into the future. You might think that that means, that means that we're due to have an impact like this once every 1,000,000 years. Well, no, that's not really why this picture is up there. One reason the picture is up there is so that we can think, wow, wasn't it lucky that it just missed the visitor center when this particular meteor happened to hit, meteor, comet, whatever it happened to be. The other point is that the Earth gets hit every once in a while with rocks that produce craters, but they get weathered because of the Earth's atmosphere, because of wind and rain and weathering phenomena. You would eventually lose this. So if this happened 1,000,000 years ago, which it didn't, it's more recent than that, if that had happened 1,000,000 years ago, it would almost have been wiped out by weathering phenomena. So we're not expecting to find any craters on Earth that are many millions of years old, simply because we won't see them anymore. And you might say, well, yes, that's a property of the Earth, but that's not true of other bodies in the solar system that don't have an atmosphere. For instance, the moon. Surely any impact on the moon will last forever. Well, strictly not so, because if we think about, for instance, the Apollo footprints on the moon, they are not going to last forever. Again, we're talking about 10 to the 6 years. For instance, the footprints on the moon are going to disappear on a timescale of 1,000,000 years, not because of weathering in the sense of wind and rain, but because the moon is continually bombarded with micrometeorites. And that is continually, effectively, churning up the, I would want to call it topsoil, but it's not strictly soil, it's the regolith. It's effectively pulverized rock on the surface of the moon. And so because that will continue for millions of years into the future, signs of, for instance, the footprints will eventually fade. And it's been predicted that even the metal hardware of Apollo, if you go far enough into the future, the micrometeorites will effectively pulverize all of the Apollo hardware and leave it almost indistinguishable from the regolith. We're now 10 to the 7 years into the future. And we're thinking about the Pioneer 10 plaque. Remember, Pioneer 10 will have left the solar system and passed stars by now. But the 10 to the 7 years is, roughly speaking, the scale over which the plaque will survive. On Pioneer 10 and 11, there's a plaque shown here on the left-hand side indicating the size of humans relative to the spacecraft, and a pulsar diagram saying this is where Earth is in the galaxy, and a little schematic of the solar system at the bottom there. And we came from the third rock from the sun. This spaceship came from the third rock from the sun. But after 10 to the 7 years, it'll be almost impossible to read this plaque, because although in principle it will last a while, it won't last forever. Space is not empty. The interstellar medium is full of tiny little particles, and if you are flying at great speed for 10 million years, you are going to hit so many objects, or so many objects are going to hit you, that effectively there will be a lot of puncture marks in this plaque, and it will be almost impossible to read. So after 10 million years, Pioneer 10 will have passed quite a few solar systems and may have passed through solar systems with Earth-like planets. But after 10 million years, anybody who picks up the spaceship, which is still going to be going, will probably not be able to tell where it came from because it will be impossible to read the plaque itself. Another factor of 10 into the future. Now we're at 10 to the 8 years, 100 million years into the future, and we're thinking about Saturn's rings. But perhaps it helps to think about, before we think about the future, where Saturn's rings came from in the first place. One thought is that the moon Mimas actually made Saturn's rings. And if you look at a moon like Mimas, you might think to yourself,
that's no moon, it's a space station.
Because it certainly bears a resemblance to the Death Star. But it is thought that maybe Mimas looks the way it does because it was pulverized in its early history, formed Saturn's rings, and what was left over then became the moon Mimas. So simulations have been done, and we've taken here a planet the size of Saturn with no ring system, take a moon, forget about the other moons, pulverize the moon, let's assume it gets hit by a comet or something like that, and the moon gets pulverized. What happens to all the debris? Notice that after a few hours it gets spread around the orbit of the moon. But even after a few days, here 2 weeks or so, it's already looking like it's forming a ring system. It takes no time at all, if you start with a pulverized moon, for that material to spread out around the orbit and produce something that looks a little bit like a ring system. And if you wait for millions of years, the various particles in the ring system slowly migrate inwards. And that's, of course, what we see today. So if that's what we see today, but we think that this formed from a load of individual small particles that are continuously raining down on Saturn's surface, all of the ring particles are getting closer and closer to Saturn until effectively they're engulfed by Saturn, then presumably that process is still continuing. So if we go into the future, many millions of years, perhaps 10 or 100 million years into the future, that process of the ring material raining down on Saturn will keep continuing, and eventually Saturn's rings will be no more. So make the most of it. For those that like Saturn's rings, like observing or like photographing, get in now, because in another 100 million years there might be nothing there to see. On a similar scale of 10 to the 8 years, what's going to happen to the solar system in 10 to the 8 years? We tend to think of the solar system as clockwork. If we know where Jupiter is now, and we know how fast Jupiter is moving, then it's easy to work out where Jupiter is going to be next year. We can put it into our app, our Stellarium, or our Sky Safari, or whatever, and we can work out where things are. Or we can turn the clock back and say, where was Jupiter when Christ was born? We can turn the clock back 2,000 years. So we tend to treat the solar system as clockwork. But we should remind ourselves, despite the fact that orreries deliberately make it look like clockwork, and Tellurian that talk about how the moon goes around the Earth and how the Earth goes around the sun, despite the fact that these are all made with gears, we perhaps tend to forget the fact that the solar system is not clockwork. On timescales of 10 to the 8 years, we cannot predict where the planets are going to be. We're not even sure if a given planet is still going to be in the solar system. Ultimately, on long timescales, the solar system is a chaotic system. We think the solar system of many millions of years ago was different to what we see today, and there's no way to predict what it's going to be on these timescales in the future. It could be that Saturn and Jupiter change places. It could be that Jupiter throws other planets out of the solar system. So don't be fooled into thinking that just because we like to think of it as clockwork, it is. On long enough timescales, everything is chaotic and actually unpredictable. still on the same time scale of about 10 to the 8 years into the future. There's us, the sun, that yellow dot, relative to the rest of the galaxy. We are sitting in a sort of galactic spur, sitting in between two spiral arms. We're in a part of the Milky Way that isn't particularly heavily populated with stars. So when we look out in the night sky, we see a few thousand stars with the naked eye, and of course more if we use binoculars or telescopes. But as the Milky Way rotates, the sun is going to end up in a different part of the Milky Way, and in the future, the sun is going to migrate into one of these spiral arms. So we're going to move from a low density region, which we're in at the moment, into a much higher density spiral arm. In other words, we're going to have many more stellar neighbors. Compared to the number of stellar neighbors we have, how many stars are there 4 light years or 6 light years or 8 or 10 or 20 or 100 light years from where we are? That number is going to increase because we're going to be in a denser part of the Milky Way. What's the consequence of being in a more crowded part of the Milky Way in the future? Well, one of the consequences is, just like Gliese 710, when it comes towards the sun, is going to disturb the Oort cloud and send lots of icy particles into the solar system, and we're going to have loads of comets and asteroids raining down on the Earth and the other planets in the inner solar system. That's going to happen if we have more stellar neighbors. That's going to happen more often. And we can see that the number of times that we have objects hitting the Earth producing extinction level events and loss of species, we can see that if we look at historical records, then the loss of species from the fossil record tells us that we have spikes every once in a while, very roughly every few 100 million years, we get sudden increase in the number of extinction level events that gets rid of some of the life on Earth. And it is thought that that is a consequence of the sun going through a spiral arm of the Milky Way, having many more stellar neighbors, which then upset the Oort cloud and produce a whole load of asteroids and comets coming our way. The one on the very right there, labeled KT, at about 60 or so million years before the present, that's the one that killed the dinosaurs, the KT, the Cretaceous Tertiary boundary. 65 or so, 66 million years ago, that's the one that killed the dinosaurs. But you can see there were many others before that, and notice that it usually wipes out tens of % of the number of species on Earth. So when we are in a spiral arm of the Milky Way rather than where we are now, we can expect to get more extinction level events. So here's a graphic interpretation of what that might look like. Almost certainly in 100 or so million years, there will be some big rock or comet heading our way. This particular one looks like it's on course to hit Italy by the looks of it. So that's bad news for Italy, but of course any large rock that hits the Earth is going to wipe out a huge number of species on Earth, not just where it hits. The entire globe is going to be affected. So almost certainly on this timescale, there will be extinction level events. There will be species exterminated. What we can't predict is whether one of those species will be us, or whether we could perhaps survive that. It depends on how big the rock is, where it hits, etc. Let's assume we're still around for a little while, beyond 10 to the 8 years. We still have other dangers of having lots of stellar neighbors. One of the dangers is they perturb the solar system and we get rocks thrown our way. But also, now that we've got lots of stellar neighbors, maybe one of them decides to go supernova. At the moment, we haven't got any candidates close to us that are likely to go supernova. But when we have many more stellar neighbors, perhaps we're much more likely to have a local neighborhood star that perhaps could be a candidate for supernova. Any supernova that goes off within 100 light years of Earth would be a considerable danger to Earth. So Betelgeuse at 600 light years, we can probably survive that okay. But a supernova at only 100 light years, there would be a significantly greater flux of radiation, and that would be a danger. It is thought that if a supernova goes off within 20 light years of the Earth, that could conceivably end all life on Earth. In other words, there would be nowhere to hide. So is it likely that any particular star is going to go supernova at that distance? Well, it has happened before when we look at the record. When we look at deposits of Earth sediments, we find that there are particular isotopes in the sediments that indicate that supernova have gone off, because supernova leave deposits of a particular isotope called iron-60. And iron-60 is an isotope of iron that after a few million years changes into something else. Iron changes into cobalt, which then changes into nickel. The point being that iron doesn't last that long. So if we find any iron in the Earth's sediments, it can't have been there from when the Earth was formed, because after a few million years, that iron changes to something else. So if we find that particular isotope in the sediments of the Earth, that means that must have been put there within the last few million or 10 million or 100 million years. So we know supernova have gone off not far from the Earth and have left this telltale signature in the sediments of the Earth. So we know it's happened in the past, so there's no reason not to think it can't happen in the future. So we're just keeping our fingers crossed that if we do have a supernova, it's far enough away that we can enjoy the spectacle and not worry about the radiation that would come pouring down on the Earth. Coming back to my old favorite, what's the Earth doing? We're at 10 to the 8 years. We are now 100 million years into the future, and all of that time the Earth has been slowing down because the moon has been tugging on it. Tidal friction, it's sometimes called, tidal pulls. The moon is effectively robbing the Earth of some of its angular momentum. It's a transfer process. The Earth is losing angular momentum, the moon is gaining angular momentum. So the Earth is slowing down, its spin is slowing down, and the moon orbit is increasing in size. The length of the day is not now 24 hours and a bit, the length of the day is now 25 hours. So forget the idea of adding a leap second every now and again, that just doesn't work. We have to redefine what we mean by a day. Whether we still attempt to divide the day into 24 hours, or whether we go decimal and start talking about a 25-hour day, we have to change the way we think about running our clocks. So the Earth is slowing and the moon is getting further away, and one of the consequences of the moon getting further away is we can no longer have solar eclipses, no longer have total solar eclipses. At the moment, as you all know, we have this coincidence that the apparent size of the moon matches roughly the apparent size of the sun, and so the moon can just cover the disk of the sun, and we can get a total eclipse of the sun. But if the moon moves further away from the Earth, of course, it'll be the same size, but further away means it won't appear to be big enough in our sky to cover the disk of the sun. So all we'll ever get in the future are annular eclipses, because the disk of the moon will always leave a bit of sunlight around the edge. It'll never be large enough to cover the disk of the sun. So again, anybody that fancies a bit of eclipse chasing, anybody that wants to see a total eclipse, do not wait. You have only 10 to the 9 years before you can never see one ever again from the surface of the Earth. A second consequence, a little more serious perhaps, other than not getting total eclipses, if the moon is further away from the Earth, we lose the stabilizing influence from the presence of a relatively large object close to the Earth. So we know that the moon tends to stabilize the axis of the Earth, otherwise known as the obliquity. So historical records tell us that the tilt of the Earth, currently about 23.5 degrees or so, has never changed by much. Historical records say it's only changed by about a degree or so, either side of 23.5. In other words, this little cartoon on the left shows the variation of the Earth's tilt, and you can barely see it. It's only about 1 degree difference over historical records. However, if the moon gets further away, which it will do on this timescale, the moon will no longer be able to stabilize the Earth's axis, and the Earth's axis will then be able to tilt a little more erratically. In other words, it is quite likely that once the moon is, let's say, 25% further away on this timescale, it will not stop the Earth's axis from changing, and it won't keep it locked in the 23 degrees that it is at the moment. It could then start changing erratically and end up like Uranus with a tilt of 90 degrees perhaps, or almost any angle in between. And of course, that will mean wild changes to the climate. Again, despite mankind trying to avoid changing the climate unintentionally, there will be changes to the climate which we have to deal with, and these are going to be really serious in the future. On the same time scale of 10 to the 9 years, what about Voyager's disk? In other words, Voyager, like Pioneer, which had a plaque on it saying, "We are humans, this is where we come from." Voyager had a gold disk. In this case, rather than pictures, it had recordings of Earth, greetings from various world leaders, plus music from all over the globe, including Liverpool, of course. The Beatles were on there. What does 10 to the 9 mean? We had 10 to the 7 for the Pioneer plaque. In other words, after 10 to the 7 years, the Pioneer plaque got so eroded it wouldn't be possible to read it anymore. So why is the Voyager plaque different? Well, record. The Voyager record shown on the right-hand side is thought to hopefully survive for 1 billion years, not a mere 10 million or so years, mainly because it is protected by a cover. In other words, the disk isn't exposed to the interstellar medium. The actual disk, the actual record, is protected behind a cover. And it's the cover that's going to be pitted by erosion. So that means the disk is protected. The record is going to survive perhaps 1 billion years. The catch is the cover contains the instructions as to how to play the record. So as well as saying we came from here, a little pulsar map, there's also instructions as to this record needs to be turned at this speed and then use this stylus to go into the groove, and the vibrations of that groove played at this particular speed will give you the music of Earth. Maybe they could figure that out from themselves, but they will not be able to read the instructions after 1 billion years. Bear in mind, remember, that Voyager is going to pass the nearest star after a few tens of thousands of years and will continue passing stars every 10,000 years or so. So by the time we get to 1 billion years, Voyager will have passed either near to or through thousands upon thousands of solar systems. And if any of them have life and are wondering why this spaceship is going through their solar system, maybe they'll pick it up and have a look. But if none of them do, then after 1 billion years, they're going to find it tricky to work out what this particular space probe was all about. We're still on a time scale of billions of years into the future. Things are going to start getting rather tough for the Earth. The first thing that's going to do to give problems for the Earth is that the sun is going to grow in luminosity. It's not a red giant yet, but as it starts to puff up and starts to go into its red giant phase, the luminosity of the sun is going to increase. And it's going to increase at the rate of something like 10% for every billion years. And a 10% increase in the luminosity of the sun is going to give serious problems to the surface temperature of the Earth. It won't be long before the surface temperature of the Earth rises to something like 80 Celsius. So basically the oceans are going to be pretty close to boiling off at this point, and it's difficult to see how mankind can survive on the surface of the planet. Who wants to go underground if you've got to go underground for another 500 million years before things get better again? So at this point, I think we'll have to say goodbye to the Earth and find somewhere else to live for a while, and at least until things cool down again. So we know that the sun is going to expand into a red giant, and if we think of the sun expanding to a red giant where the size of a red giant could be conceivably the same as the orbital radius of the Earth, then you can see that, well, that could be a problem. If we are that close to the surface of a red giant star, it's going to get pretty damn warm. And one question is the sun going to expand and engulf the Earth? Is it going to expand to the point where the radius of the sun is greater than the radius of the Earth's orbit? It is thought probably yes. But that doesn't mean the Earth will be engulfed, because there are other things you have to take into account. Yes, the sun is going to expand, but there's going to be an enormous solar wind. The amount of material coming out of the surface of the sun is going to be enormous, so the sun will be losing mass. If the sun loses mass, according to our understanding from Newton as to how objects orbit around other massive objects, if you lose gravitational pull, the orbit tends to get larger. So in this cartoon on the left, the sun is expanding, but because it's losing mass, the Earth is actually getting further away from the sun. So yes, the sun will expand until it engulfs the orbit of the Earth. But the Earth isn't there anymore. By the time it does that, the Earth will have moved out, possibly to where Mars is. So yes, the original Earth orbit gets engulfed, but the new Earth orbit is probably going to be outside the sun, and maybe the Earth will survive. Different people have different ideas. You have to take into account not only the solar wind, you have to take into account tidal effects as well. So the jury is still out as to whether or not the Earth is going to survive the red giant phase of the sun. Once the sun has done its stuff, now we're talking about many billion years into the future, the sun's fuel will last for probably 5 billion years or so. It's about 5 billion years old. The fuel is good for another 5 billion. We're about halfway through the sun's lifetime at the moment. But once it's been through its red giant phase and sloughed off its outer atmosphere, what's left, the core of the sun, is what we call a white dwarf, a very hot object about the size of the Earth, give or take a bit, and probably made mostly of carbon. In other words, hydrogen will have been fused into helium, helium will have been fused into heavier elements, and we're left with probably a large chunk of charcoal. It is thought that maybe the pressure is so high in the center of the white dwarf, it might not be just carbon or charcoal. It is conceivable that it might actually be a solid diamond, but we're not actually too sure of that. Astrophysicists disagree as to what's at the heart of a white dwarf. If the Earth survives, there are still problems. Even surviving the sun going through a red giant, there are still going to be problems. The core of the Earth is going to cool down. The core of the Earth is not kept warm by the sun. The Earth core is molten, but it's got nothing to do with radiation from the sun. The core of the Earth is molten because of radioactive decay of elements that have been around since the Earth was made 5 billion years ago or so. But at some point, the radioactivity in the core of the Earth will not be enough to keep the core molten. And as soon as the core solidifies, we no longer have a dynamo. If we don't have a dynamo, we don't have a magnetic field. So at some point in the future, the Earth is going to lose its magnetic field. And if it loses its magnetic field, it'll be exposed to radiation, not necessarily from the sun, but from cosmic rays, and as a result could easily lose its atmosphere, even if it hadn't already had this battering from the fact that the sun has expanded to a red giant. It's thought that this might have been what happened to Mars. At least it was a contributing factor. Mars is much smaller than the Earth. Its core would have cooled before the Earth's core cooled. So Mars lost its magnetic field a long time ago simply because it was smaller. And if Mars lost its magnetic field, even if it had an atmosphere in its early history, once it lost its magnetic field, it found it very difficult to hang on to its atmosphere because of radiation from cosmic rays. So in a sense, the Earth will undergo the same fate as Mars in the future, even if it survives the red giant phase of the sun. And if that wasn't enough, along comes Andromeda crashing into the Milky Way. The Andromeda galaxy, on timescales of a few billion years, just about the same time that the sun is going through the red giant phase, the Andromeda galaxy is going to come hurtling towards us. So in about 3.7 billion years into the future, the Andromeda galaxy is going to appear huge in our sky as it gets closer and closer to us. And after 3.8 billion years, they start to interact with each other. It's unlikely that the sun will actually hit anything in Andromeda. Most stars will pass through each other, but all of the gas and all of the dust will interact, and there will be a riot of new star formation as the two galaxies passed through each other. So in other words, our sky will be lit up with new stars being born as these two galaxies pass through each other. They'll probably pass through and temporarily come out the other side and then eventually settle down and merge with each other. But after 4 billion years, Andromeda will have passed through us and come out the other side. And after 5 billion years, basically we will be, if we still exist, we will be in a galaxy which is the merger of Andromeda and the Milky Way. We'll have to decide what to call it. Is it going to be Milkdromeda, Andromeda. We've got 5 billion years to come up with a new name for that galaxy, which is a merger of the Milky Way with Andromeda. But it is not going to cause us a problem. It might sound cataclysmic to talk about galaxies colliding, but if Andromeda collides with the Milky Way, which it looks like it is definitely going to do, the Sun will probably survive. If the Sun gets pulled out of the Milky Way, which is possible, it'll take all its planets with it. In other words, it's going to be such a slow process over billions of years, or at least hundreds of millions of years. If the Sun does get pulled out of the Milky Way, the planets will simply go along for the ride. So if the Earth survives the red giant phase, if the Earth survives lots of its magnetic field, colliding with Andromeda is not the end of the line as far as the Earth is concerned. If the Earth does survive, then after 10 to the 11 years, we're now talking 100 million years into the future. Sorry, we're talking 100 billion years into the future. This looks like a sort of Photoshop. Actually, it's a photograph from the Deep Space Climate Observatory. That's a genuine picture of the Earth and the Moon taken from a considerable distance, which is why it looks a bit odd. Of course, from our perspective, that's the far side of the Moon, because we always see the other side, so it doesn't look as we normally see the Moon. But this far into the future, the Moon will have continued to slow the Earth to the point that one day is the same as 1 month. In other words, the length of time it takes the Earth to rotate once, which is what we normally call a day, will be the same as the length of time it takes the Moon to go around the Earth, what we normally call a month. So 1 day is equal to 1 month. So any particular point on the surface of the Earth will always see the same Moon. In other words, the Earth is tidally locked to the Moon. Half of the Earth will always see the Moon, and half of the Earth will never see the Moon, because the Earth and the Earth will rotate and the Moon will go round the Earth lockstep. And so they'll always be in the same relative position. So one side of the Earth will always face the Moon, just like at the moment one side of the Moon always faces the Earth. Eventually it'll be true the other way round as well. They will be completely tidally locked together, a bit like Pluto and Charon are at the moment, but it's going to take a long time for the Earth and the Moon to get into that particular lockstep. But it will eventually happen, assuming the Earth and the Moon survive all the other things that have been coming up till now. Okay, we better move into the future. All of the galaxies in the local group are going to merge together. So we've already said that Milky Way is going to collide with Andromeda. There are lots of little satellites around the Milky Way. So we know that the local group at the moment is Milky Way, M31, the Andromeda galaxy, M33, the Triangulum galaxy, and 100 or so little dwarf galaxies. All of these eventually are going to merge into one mega galaxy. What about all the other galaxies beyond the Milky Way? Well, we know, for instance, that even galaxies that are receding from us, even because of the expansion of the universe, galaxies that are receding from us faster than the speed of light, we can still image those. This was a lockdown challenge that I tried in 2020 to actually take a picture without using a telescope of a galaxy receding at twice the speed of light. So we know that it is possible to image galaxies now, even though they are very distant and moving very fast. If we look on the right-hand side, there's the Hubble Ultra Deep Field, a picture of the sky where Hubble exposed for 1 million seconds and realized there's an awful lot of galaxies out there. Tiny patch of sky, but there's still thousands of galaxies. But there will come a time, 10 to the 12 years into the future, where the universe is expanding so fast that it won't be possible to see distant galaxies because they will be too distant and moving away too fast. So it's sobering to think that if a civilization in the future built themselves a Hubble Deep Field telescope and took a picture equivalent to the Hubble Deep Field, they would only see the stars in their own galaxy. For instance, those two stars, which is what the Hubble Deep Field would be if we took away the galaxies and only left the stars in the galaxy. So in other words, a civilization that comes into being many billions of years into the future, even if they had the technology to build really sensitive telescopes, if they look into the universe, they would see nothing other than their own galaxy. They would not be aware of the fact that the universe was full of trillions of galaxies. They would only be aware of the fact that they were living in a galaxy of a certain number of stars. And it doesn't matter what their level of technology is, they would not be able to observe anything beyond their own galaxy. That's a rather sobering thought. Returning to where I started, we know all the hydrogen in the universe was made in 3 minutes. But we're now 1 trillion years into the future. All the hydrogen was made in 3 minutes, but after 1 trillion years, it's running out. And it's not going to last forever. And some people have said no new star formation, though some people have said, well, maybe for a little while stars will be made out of something other than hydrogen. Rather than using hydrogen to make new stars, maybe they'll start using some heavier elements, some heavier gases to make stars. It's been hypothesized, no proof, but it's been hypothesized that it is possible to make a star from heavy elements in which there are nuclear fusion reactions in the core, but the surface temperature is well below the thousands of degrees that we're used to. Maybe it's possible the surface temperature might only be hundreds of degrees. In other words, it is possible to be as low as 200 Kelvin. In other words, it could actually be below the ice point. A star with nuclear reactions at the core, but the surface temperature is such that the surface could be frozen. And when we're talking about frozen stars, this is not what I mean. So that's Disney's version of Frozen. If that's the picture you've got in your head, just let it go. Because what we're actually talking about is stars in which there is ice in the outer part of the star, which is a rather amazing thought, but this is just hypothetical. And before we can really make any progress, and yes, I still have a few minutes to run yet, we need to think about what the universe is going to do. And we don't know, but we have a good idea of what the universe is going to do. These lines indicate how big the universe is as a function of time. That's where we are now. The universe is of size 1. Doesn't matter what that 1 is. And in the past, the universe was smaller and was presumably 0 size at some time in the past, depending on which of those colored lines represents the universe. Each of those colored lines represents a different amount of stuff in the universe. If the universe has got a lot of matter in it, then the expansion of the universe going up and up and up to the right, you can see starts to come down again. If there's a lot of matter in the universe, it'll all come together in a big crunch tens of billions years into the future, and the universe will be closed. But the evidence is that's not the universe in which we live. We think the amount of matter in the universe is such that we're actually following the red line. Not only is the universe expanding as we go into the future, the expansion rate is getting faster and faster and faster as this line goes up and up and up and up. So we think we live in a flat universe, but it's expanding at ever accelerating speed. That's the evidence that's come out of the last 20 years or so of observations. So we don't think the universe is going to end in a crunch. We think it's going to continue expanding, as far as we can tell, forever. And for the far future timeline, which I'm going to go through fairly quickly as I'm aware of time here, instead of going up a factor of 10 in each box, now each box represents 1,000,000 times further into the future. This is getting really difficult to keep your head around. So I'm not going to start talking about numbers of a zillion years or a gazillion. I don't know what these numbers are. We're just going to rely on the fact that it's 10 to a very big number, and we're going to look at how that big number changes as we go through the future. So where did we leave the universe before we took this aside and asked, is the universe expanding forever or not? We said all the hydrogen was made in the first 3 minutes, but is running out. Stars have a finite lifetime. They may last for trillions of years, but it's a finite lifetime. So if we made all the hydrogen 13.8 billion years ago, and after a few trillion years it's starting to run out, what does that mean? there will come a day when there are no more stars. The age of starlight will come to an end on roughly this scale. Don't take the numbers too literally, just ballpark figure. The stars will still be there. They're no longer shining. They've run out of fuel, so they can't shine anymore, but they're still there. The mass is still there, orbiting the Milky Way or whatever other galaxy they're in. So these dead stars are just drifting through space like zombies. Stars like our sun, when it comes to the end of its life, white dwarfs, there will be neutron stars, black holes, etc. But they won't be shining in the conventional sense of nuclear reactions will not be powering them anymore. White dwarf stars might look white to start with just because they're hot, but they're going to cool off. In other words, they become black dwarfs. And if that picture isn't very clear, let me make it a little bit brighter. Basically, a white dwarf will just be a lump of carbon. Whether it's diamond, whether it's graphite, who knows. But it's just a lump of carbon which eventually will just look black. Stars that aren't ejected from the galaxy, some of them, because of the way they move around the central black hole, might be ejected from the galaxy. All others will be eaten by the supermassive black hole at the center of the galaxy. Recent observations made by SoU3A, the Stratospheric Observatory for Infrared Astronomy, in other words, the 747 with a big telescope in the back end, that has actually mapped out magnetic fields in a galaxy, and we can deduce that if we know what the magnetic fields are doing, we think all of the matter is being funneled by the magnetic fields into the supermassive black hole at the center of the galaxy. It's a shame to realize that SoU3A has now been decommissioned. After many, many years of service, that 747 is no longer doing infrared astronomy. But
pilot was a woman.
Is that right? So observations like this are telling us about the magnetic fields and about the process by which matter is going to end up inside black holes in the future. When we think about what these various stars are made of, they're made of atoms, well, maybe not neutron stars, but atoms are made of nucleus and electrons, and the nucleus is made of protons and neutrons. But it is thought that maybe protons decay. Protons aren't necessarily stable, and if protons do decay, that means every atom in the universe is going to fall apart, in which case every piece of matter in the universe is going to fall apart. Now, we don't know what time scale this is going to occur over. It is thought that if protons decay, they don't decay on time scales less than 10 to the power 36 years. A ridiculously long time, but it's still possible to calculate. If the protons don't decay, then eventually even black dwarfs are going to evaporate. So atoms will survive in white dwarfs for a while, or black dwarfs for a while, but even they will evaporate, and hence we'll end up with no atoms in the universe whatsoever. Black holes will merge together as galaxies collide with each other. The supermassive black holes at the center of the galaxies are going to end up merging. And so we'll end up with supermassive black holes, not of millions of solar masses, or even billions of solar masses, but perhaps we'll end up with black holes which have a mass of trillions of solar masses as they all start merging with each other. But black holes are not eternal. Black holes do not last forever. They evaporate on timescales that are ridiculously long. Notice our red square there is creeping ever further over to the right-hand side. Why do black holes evaporate? Well, this is a quantum mechanical process, and very roughly we can say that, okay, you can borrow energy from nothing and you can make matter and antimatter, particles and antiparticles, as long as they annihilate and pay back the loan very quickly. In other words, you can take energy, generate matter, and then they annihilate and they generate energy, and you're back to square one. The universe hasn't noticed that you've borrowed energy from nothing, made matter and antimatter, and then they've annihilated back to energy again. That concept, some people believe, is how the universe came into existence in the first place, but that's a slightly different story. Why is that relevant to black holes? Well, if this idea of borrow energy, make matter and antimatter, and then they annihilate with each other, what if that process happens very close to a black hole? It is possible to borrow energy, make matter and antimatter, one of them gets sucked into the black hole and the other doesn't. So you end up with, well, what does that look like? It looks like something has come out of the black hole. And that is what we believe is Hawking radiation. Hawking proposed this. We've got no proof of this, but many theorists believe that this is what's going to happen to black holes. Smaller black holes evaporate faster than large ones, and so as a black hole evaporates, it radiates and gets smaller and radiates and gets smaller, and the smaller it gets, the faster it radiates, and so a black hole evaporates with radiation levels increasing until right at the end there's a flash of radiation as it disappears. Even the very large ones, even the supermassive black holes, even a black hole with a mass of trillions of solar masses, even though Hawking radiation will make it radiate and make it evaporate very slowly, if you wait long enough and look at the red square, we're now talking about even more ridiculous times into the future, even supermassive black holes will will evaporate and will be no more. It'll take trillions of times longer than for small black holes, but it will eventually happen. And as far as we can tell, the entire universe will have evaporated into a bath of radiation. What some people would call the heat death of the universe. There's no matter left. There's just radiation floating around the universe. So is this what we mean by the end of time? Well, virtually. You can't define infinity, you can't define eternity, but you could take this as a sort of endpoint. 10 to the power 100 is a Google. Not that one, the other one. Google with an L-E is a misspelling of Google with an O-L. 10 to the power 100 is Google. And after a Google years, 10 to 100 years, all the black holes have gone and there is nothing left other than a little bit of radiation floating around. In other words, nothing interesting happens ever again from this point onwards. There's just continued expansion of the universe. The radiation that exists will continue to float around, but there's no matter left in the universe. And so time becomes arguably pretty meaningless. We're getting depressed now, aren't we? Yes. I don't often do this, but just to put it in perspective, that's what a Google is. 10 to the power 100. A million is 6 zeros, a billion is 9 zeros, a trillion is 12 zeros. 10 to the power 100 is just silly, but still you can do calculations on that scale. Where does that leave us? Well, eternity is a very long time, especially towards the end, as said by Woody Allen. But one quote I like is, it's difficult, of course, to put a human timescale on something which is 10 to the power 100 years. But I like this quote from a cartoon I particularly like, which says, really, a human is really just a system for converting dust billions of years ago into dust billions of years from now, via a roundabout process which involves checking emails quite a lot. So that's depressing. The universe is going to come to an end, and it's going to be really, 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 really boring when it does, because for the rest of eternity, Google might sound like a large length of time, but eternity is much longer than that, and nothing interesting happens beyond a Google years. For the rest of time, nothing interesting happens, unless we've got our laws of physics wrong. So rather than leave you on that depressing note, let me try and finish on a slightly more upbeat note. Currently, we live in a golden age. The sun is middle-aged, 5 billion years old, another 5 billion years left. It's middle-aged and stable and well-behaved. And we have a moon that's at just the right distance to give us total eclipses of the sun and to give us a stability to the axis and a stability to the seasons. So the moon is our friend and is doing a lot for us. And thanks to evolution and a few billion years, we, standing here on planet Earth, are able to explore and discover and understand the universe. And we can do that by visiting some of our closest neighbors or building ourselves telescopes in which we can study galaxies that are billions of light years distant. We couldn't have done this a long time ago. Mankind couldn't have existed in the early universe because we needed multiple generations of stars to make the heavy elements that are essential for the sort of life that we understand. We needed stars to fuse hydrogen into helium, and then more stars to fuse helium into heavier elements, because we need carbon and nitrogen and oxygen and phosphorus and calcium and all these other elements to make us who we are. So we couldn't have existed in the very early universe. And we've just seen that trillions of years from now, the universe is going to be very, very, very boring and very dark. So you could say, what's the best time to exist? And I would argue, it's now. Thank you for listening.